Hello, so in the last video on the playlist we looked at intuition behind what curved spacetime is, with lots of strange thoughts experiments involving cats falling through very high towers. And if you would like to check out my not so impressive artwork, would recommend checking out that video. You'll see a very interesting, shall we say, illustration of a sketch of cats. I'm not the best artist, it must be said. But anyway, in this video we're going to be looking at more of the maths of general relativity. So last one was more physically intuitive, and I'll put the link to the last video in the playlist in the description of this video. But in this video we're going to be looking at the maths accompanying our physical intuition of surfaces and curved space-time. And so we're going to be talking about geometrical objects that live on manifolds of surfaces. So we'll be talking firstly about vectors. So if you've looked at the special relativity playlist, you'll see that a lot of relativity concerns vectors, and special relativity is heavily concerned with vectors. Special relativity also is concerned with the size of vectors, so it's concerned with the metric. The metric associated with special relativity is called the Minkowski metric. But we're going to talk about vectors and metrics more generally here, so we can integrate them into curved space-time later on. And also we'll talk a little bit in this video about a vectorial-like object called one-forms, which have some rather unique and cool properties. So I hope you enjoy this video, and I'm looking forward to getting going with you on the wonderful world of geometry and applying it to relativity. So if we're thinking to the most straightforward geometrical object we can draw on a manifold, so on a kind of surface, the simplest one we can kind of consider is a vector. Now a vector can have a number of dimensions associated with it, but usually when we think of a vector we think of an arrow, and an arrow only has a length as well as having direction. So an arrow is an example of a one-dimensional vector. We could consider vectors of higher dimensions if we want to, and those vectors might have areas or volumes, but if we're sticking to a one-dimensional vector we're dealing with an arrow, and the arrow will have its length and a direction associated with it. And we can kind of be a bit more specific about what a vector is. So we've said it has length and direction, at least if we're dealing with a one-dimensional vector. But it's worth saying this vector could be embedded in higher dimensional space, like if you draw a vector on a whiteboard, the vector is one-dimensional because it just has a length, but the whiteboard is two-dimensional because it has area. So, a vector might be living in a higher dimensional space. But, as well as a vector having length and direction, if we draw a vector, no matter what coordinate system we use to represent that vector should look the same. We should ultimately be describing the same vector, and that's very important. And that gives a vector a very particular relationship between the components we use to represent the vector and the basis vectors we use to build the vector. But before we talk about that relationship, let's introduce our components and our basis vectors. So if we've got a vector, an overall vector, I'll usually use an arrow over it to tell me I'm talking about an overall vector, and it's equal to the sum over mu, so the sum over our kind of coordinates of a mu, so the component of a along the muth axis, times e mu, so the basis vector along the muth axis. And the basis vectors give a direction, and the components can allow me to find how large A is. And so we'll see that the components, the components, once I've got a coordinate system, the components tell me how big A is going to be, and A mu tells me how big A is going to be along the spatial axis. But let's have a look at what happens if I play around with my components and my basis vectors. So let's imagine I've got two coordinate systems, and both coordinate systems I'm trying to describe a rod. And the rod I'm trying to describe is this blue rod, and it's the same for coordinate systems. Now this rod is orientated along an axis, and it has a length, so we can think of this blue rod as a vector. Now I've drawn the rod twice. In the top and bottom image it's the same rod, and therefore has the same length. Now in the top image I've got quite large basis vectors. But to go to my bottom image of the same rod, I've gone to a coordinate system where my basis vectors are smaller. And my basis vectors are the chunk of the rod that is split up by that kind of purple wedge. So in my top image, I've got two basis vectors that I add together to get my overall vector. But in my bottom image, I have to stick four basis vectors together to represent the same rod. So we can see if we halve the size of our basis vectors, so if we split our basis vectors into two, the number of components actually double. So if we make the basis vector smaller, the components get bigger. And that's a very important property of a vector. So a vector, we can also say, has a contravariant relationship between its components and its basis vectors. If the components get bigger, the basis vectors get smaller, and vice versa. Now, I've shown that visually in a hopefully fairly convincing way, but you might like a bit of mathematical proof. So if you want a bit of proof, I'm going to do that just now. But if you want to move on to the next part of the video, I would encourage you to do so also. But it is important to know a vector not only has length and direction, it also has a contravariant relationship between its basis vectors and components, and that makes a vector very different to another object that has size and direction called a one-form that we'll come on to at the end of this video. But anyway, for now, I would like to present a mathematical proof to justify what I've said about the contravariant nature of a vector. But if you would like to skip the mathematical proof and are happy with the pictorial description, then by all means move on to the next part of the video, where we'll look at how the components of a vector transform when going from one coordinate system to another. But anyway, if you want the proof, so we're going to try to prove that vectors are contravariant objects. So if we make the basis vectors bigger, if we make the basis vectors smaller, the components get bigger. So to do that, we need some way of changing the basis vectors and components. So I'm imagining that the components are some function t, and the basis vectors are some function t, and t is controlling the size of these objects. And importantly, a mu as a function of t is going to be a different function to e mu as a function of t. But we're parameterizing both the components and the basis vectors in terms of t, which can control their size. Well, if we're interested in ensuring that the vector as a whole doesn't change, we can essentially calculate the derivative of a vector with respect to t, and then we can say, well, if a is a vector, dA by dt is going to be 0, because even when we change the size of our basis vectors and also our components, the vector as a whole won't change, because the vector as a whole has some coordinate independent meaning. Well, we can use the product rule to work out what dA by dt is. So just use the product rule on that first line, and setting dA by dt to 0, we can clearly see that, if we're taking for simplicity the components and the basis vectors to both be positive, just for simplicity, we can see that to ensure that our vector A doesn't change, so dA by dt is 0, if dA mu by dt is bigger than 0, so if A mu is increasing, then E mu has to be decreasing, so dE mu by dt is less than 0. And so that's a mathematical proof for the contravariant nature of a vector. So now we've explored what a vector is, so an object with, length, direction, and a contravariant relationship, therefore, between its, components and its basis vectors. Let's go on to looking at how the components of a vector change from one coordinate system to another. Because although the vector as a whole doesn't, the components, so A mu, will change between coordinate systems. So on the last part of the video, we mentioned that a vector has independent meaning, so it's the same thing no matter what coordinate system we use to represent it. And we saw how that leads to a contravariant relationship between the components of a vector in a coordinate system and the basis vectors used to express the vector within that coordinate system. But, often if we have two coordinate systems, then by constructing the coordinate systems, by definition, we construct our basis vectors for those different coordinate systems. What's much less obvious is how the components of a vector will change when we go from one coordinate system to another. And this part of the video will be devoted to finding an expression for how to go from the components of a vector A in one coordinate system to the components in a different coordinate system. And so let's say in one coordinate system, and borrowing language from special relativity, we'll say this coordinate system, we'll call it the non-prime coordinate system. So all the indices are not prime, so we have A mu instead of A mu prime. So A mu is the component of our vector A along the muth axis. Sorry, I should say along the nuth axis in the non-prime coordinate system. And we want to see how we transform that to the muth component of A, but in the prime coordinate system. So we're going from a component of one coordinate system to the component in another. We're going from non-prime to primed. And the transformation is going to have to be a kind of a object with two indices, because it's going to have to behave as some kind of matrix, because it's got to convert a list of ordered components into a different list of ordered components. And if you think about the rules of linear algebra, we'll need a matrix to do that. So if A is a vector living in an n-dimensional space, then our transformation matrix is going to be a m by n matrix. So our transformation looks something like this, and because we're dealing with relativity, we use the rule that we sum over repeated indices. So for example, let's say that A is living on a whiteboard, so the space, the manifold it's on, is a two-dimensional manifold. Then mu could be 1 or 2, and therefore for example A naught prime, so sorry, A1 prime, so the component of A along the axis I've labelled axis 1 in the prime coordinate system would be lambda 1 prime 1 A1 plus lambda 1 prime 2 a2. So you see we sum over mu. We allow mu to run from 1 to 2. So with relativity we sum over repeated indices. And accompanying this playlist I plan to do short videos where I show explicitly how this calculation works. I'm leaving this out of the main videos because the main videos are primarily conceptual. And for this video you just need to think about this transformation matrix with two indices as essentially transforming the components of a vector in one reference frame to the components in a different reference frame or different coordinate system. I'll make smaller kind of more like problem-solving videos where I go through calculations like this in more detail. Now, to get some kind of a grasp and intuition for where you might have seen this transformation matrix before, if you've done further maths and looked at rotation matrices, then this transformation matrix could be a rotation matrix. It could allow us to find the components of a vector when we rotate our kind of coordinate system to lead to a new coordinate system. If you've done special relativity, the transformation you're interested in there is still rotation, but it's rotation in space-time, so it's a rotation between the time and the space axis, or rotation over time and space axis. And because space-time has hyperbolic geometry, this rotation is slightly unusual, but in special relativity, the transformation matrix we're interested in is still a rotation. It's just a rotation in hyperbolic space. In other words, it's the Lorentz transformation, which leads to effects like time dilation and length contraction. Those things are very specific, and flat space, flat Euclidean space, and the space-time of special relativity are both flat, and therefore it's easy to come up with very concrete examples for this transformation matrix. It's harder if the surface is curved, and so I'll give a more general way of thinking about this transformation matrix. The transformation matrix is nothing but the Jacobian. Now you use the Jacobian, say if you want to go from integrating in Cartesian coordinates to integrating in polar coordinates, you'll use the Jacobian matrix, or particularly the determinant of the Jacobian matrix, to work out essentially the scale factor you have to put in front of your differentials that you're integrating with respect to go from an integral in Cartesian coordinates to an integral in polar coordinates. So, in general, this transformation matrix is a Jacobian, but particular examples are rotation matrices in Euclidean space, and also the Lorentz transformation in the context of special relativity. So we've now talked a little bit about a vector. We've talked about the components of a vector and how they transform. We're now going to bring in another type of tensor called a metric. And the role of a metric is to give distances on the manifold by connecting points with a vector and giving a length to that vector. So a metric kind of quantifies the magnitude, if you like, of vectors that live on our manifold. So the metric tensor is a tensor and therefore has coordinate independent meaning, However, the components of the tensor, so G mu nu, do depend on the coordinate system we are trying to describe the metric in. But a particular manifold, in the context of spacetime, a particular geometry of spacetime will have the same metric in all coordinate systems. However, the coordinate system we pick will determine the components of that metric. And we're going to use the metric to define the distance between 2 points, and we're saying these 2 points are connected by a vector A, so we traditionally imagine one of those points being located at the origin of a coordinate system and the other point at the tip of our position vector A, if you like to use geometrical language. Although A doesn't, A could give the distance between points in space-time. A could also be, a vector which we could use to find the size of vectors like for velocity. But we can use A and our metric to find distances on our manifold. So the distance squared is given by this equation, which involves our metric. Now, here I'm using A twice. I've got A mu and A nu. It's worth saying if we were looking at mixing up components of two vectors, so if I had A mu but B nu, where A and B are vectors on the manifold, then my equation here would give the scalar product, or the square of the scalar product, between the vectors, and that would also result in a scalar and therefore be a coordinate independent property. But going back to just thinking of a kind of scalar product, if you like, of a vector with itself, that will return for me the square of the size of the vector. And you can see that because the length of a vector or its size doesn't have any indices, it looks like the mu below the G, so the mu within our metric, and the mu above our A, so the muth component of A, the mu's cancel out. And similarly with the nus, those cancel out, leaving me with a scalar quantity, the length of a vector. So one trick we'll use is contracting, we call it contracting the indices. It's essentially the rule that if we have repeated indices, but one is above and one is below, they kind of cancel out. It's just a notation. And the notation occurs through our metric tensor, because our metric tensor is the thing that can contract indices. There's also the inverse metric tensor, which would have upstairs indices and could contract downstairs indices. But we haven't come on to objects with components which have one downstairs indice. We will by the end of this video. But for now we're just looking at metrics and its connection to vectors. And all vectors, their components have upstairs indices, and the metric will contract these. Now we sometimes write the scalar product of a vector with itself in the notation given below here. You might also, if you're dealing with special relativity, see instead of ds, delta s. I'm using ds because I'm trying to emphasize that the vectors that we're dealing with on a curved manifold, because the vector is straight but the manifold is globally curved, to keep the vector on the manifold, the vector needs to be infinitesimal, so it needs to be so small that within the region the vector exists, there is no curvature of the manifold. The manifold might be slightly at an angle, but it has no curvature, and therefore the vectors need to be infinitesimal, so the length of the vectors need to be infinitesimal. Hence ds will be, in the context of general relativity, an infinitesimal property. And we will look at how to transport vectors over the manifold, so over a finite non-infinitesimal distance, when we look at parallel transport in a later video. Now, the components of the metric tensor depend on the coordinate system used, but the length of A, and therefore the scalar product, is a coordinate independent thing. And we can actually, use our scalar product notation to, however, to get a expression for the metric in terms of the basis vectors for our vector A, and therefore define the components of the metric within a coordinate system. And that gives a good physical intuition for the components of the metric tensors, so it's worth doing. So here we've got, in the blue box, we've got our equation for the scalar product. We wrote it in terms of our metric tensor and in terms of the more traditional route, which is using a dot. So we call when we've got A dot A, we say we're taking the dot product of A with itself. It's just a more common way of writing the scalar product, which is particularly useful if we're dealing with familiar Euclidean geometry, where we just presume things about the metric through Pythagoras' theorem and don't need to worry too much about what the metric is. And then if we expand our vector A in terms of its components and basis vectors, we get this equation. And I've moved around the A mu's and N u's because these things are components of a vector, so they are themselves just numbers and we can move them around freely. We don't have to worry about the order that these components are in. And then if we cancel these components out, which we can do because they're numbers, then we get G mu nu is equal to E mu dotted with E nu. So in other words, the components of a metric tensor within a particular coordinate system is equal to the scalar product of the basis vectors of that coordinate system which are attached to the manifold. And this allows us to very quickly, for fairly simple kind of representations of the metric, because most of the time, and I think in fact, probably at least for most things we'll be dealing with, but I think for everything, we'll be dealing with coordinate systems where the components, where the basis vectors are orthogonal. In other words, the scalar product between them is zero. And that's because we're setting up independent axes. There's no overlap. Just as if something is moving vertically upwards, we say it has zero horizontal motion. So its motion in the x-axis is zero if it only has motion in the y-axis, because the y-axis are perpendicular, so that scalar product is zero. We could say a similar thing about space-time generally. The dimensions of space-time will have the word perpendicular might not be right because space-time has a weird geometry, but the space-time axes, the scalar product between any space-time axis is zero. And, well, the scalar product between any two different space-time axes is zero. The scalar product of a basis vector along a spacetime axis with itself need not be zero, and in fact shouldn't be zero. Because if it was zero, we would be saying that vectors lying along that spacetime axis would have zero length, and if we would do that for every spacetime axis, we would suddenly have a metric telling us that, our vectors within spacetime never have any length, which wouldn't make drawing these vectors at all useful. Because one of the key features of a vector is it does have length. Essentially, the scalar product of a spacetime axis with itself doesn't have to be zero, but the scalar product of the basis vectors of a spacetime axis with another spacetime axis, that will be zero. And therefore, the only components of our metric which are going to be non-zero, in our orthogonal coordinate system, if you like, are the diagonal components of our metric. So the components where mu is the same thing as nu, which referred to taking the scalar product of a basis vector with itself. And therefore, our metric being diagonal will have a fairly straightforward form, and we can even go further than that. For example, if we're looking at the metric of flat space in 3D Euclidean geometry, we know that we're using unit basis vectors that are orthogonal, so all the diagonal components for the metric describing 3D Euclidean flat space, all the components along the diagonal will have a value of 1 because we're dealing with unit basis vectors, and all the other components can be 0 because all the metrics generally we could be looking at are diagonal, can be represented as diagonal matrices. Therefore the Euclidean metric, the metric that describes flat space in Cartesian coordinates, is just an identity matrix. If we're dealing with space-time, it's a little more complex because there's a negative sign in front of the time component within our metric. But for just space, we'll just have the identity matrix as the representation of our metric for flat space. Now you might wonder if, general relativity describes curved space-time, do the orthogonal basis vectors, E mu and E nu, do they remain orthogonal as we go across our manifold, because our manifold is curved? To answer that, because the vectors that we're looking at, for them to stick onto the manifold, have to be infinitesimal, our coordinate systems are also going to be infinitesimal, and so the coordinate systems describing our curved metric are going to be infinitesimally small, and across that distance E mu and E nu remain orthogonal basis vectors. And to get a manifold, you have to smoothly connect lots of these infinitesimal coordinate systems, which is really the basis for the more mathematically abstract definition of a manifold. It's smoothly connecting coordinate systems, if you like. But anyway, we talked about the metric, and we've talked about calculating the components of a metric in one coordinate system. Now we're going to look at calculating the components of the metric in a different coordinate system. So we've looked at what the metric is. We've seen it's related to the distances between events in space-time, or distances between points on the manifold connected by a vector. And we looked at finding an equation that will tell us the components of the metric in a particular reference frame or coordinate system, where we said the metric well, the components of a metric was given by the scalar product between the two relevant basis vectors. But the metric tensor is whilst being a tensor, and so, the metric tensor itself has coordinate independent meaning, the components do depend on the coordinate system, so we need to know how to transition from giving the components in one coordinate system to giving the components in another coordinate system. So to do that, we recall that the scalar product of a vector with itself is a coordinate independent thing, and therefore when we take the scalar product, it will be the same in both the primed and non-primed reference frames or coordinate systems. And remember, when I'm using a prime, I'm just saying we're describing, in this case, the distance between 2 points using a metric, which is vectors which are in a different coordinate system, or being described in a different coordinate system. Now, we can't really go much further than this if we want to find the components of the metric in one coordinate system and compare it to the components in another, unless we can have the components of our vector A being written in the same coordinate system on both sides of the equation. So what we can do is we can use our transformation laws that tell us what we can substitute for our primed component of our vector A, and that then allows me to write an expression with just the non-prime components of vector A, and again using the fact that the components of a vector are just numbers, and therefore we can move them about freely and cancel them out very easily. We end up concluding that G mu nu would have to equal G mu prime multiplied by the Jacobian here, and then another Jacobian matrix. And it's worth saying it's really these Jacobian matrices formulae which ensure that the metric has a coordinate independent meaning, and also gives us a way to transform the components of the metric between one coordinate system and another. Now, the metric has two indices, so we can represent it as a we can represent the metric as a matrix, although we can only fill in the numbers within the matrix once we picked a particular coordinate system with which to express the metric. And also we are starting to see a pattern for how to transform tensors. So we mentioned that vectors are tensors, and we saw that to transform the components of a vector in such a way to keep the length of the vector preserved between coordinate systems, so to give the vector coordinate independent meaning, we had to multiply the components of the vector by one Jacobian matrix. So for a tensor with one indice, in other words, something like a vector, for example, we need one Jacobian matrix to transform its components. For a metric, which has two indices, we need two Jacobian matrices. And for a scalar, which has zero indices, so we call it a rank 0 tensor, we don't need any Jacobian matrices, because a scalar doesn't change at all. And therefore, in general, if you've got a rank n tensor, you'll need n Jacobian matrices to transform the components from one coordinate system to another. But after all that maths, you might wonder what's the point of transforming the components of the metric from one coordinate system to another. I mean, it's easier to visualise vectors and therefore to see perhaps why we'd be interested in transforming the components of a vector between one coordinate system and another. I mean, when we do that in the context of vectors, so 4 vectors in space-time, in special relativity, the consideration of how the components transform leads to ideas like time dilation, length contraction, lots of the weird effects of relativity. But why would we be interested in how the components of the metric transform? Well, it's really because, it's not very common that a mathematically simple model, or the simplest mathematical model, is also a very physically useful mathematical model. So in the context of metrics, we might, for example, want to use a coordinate system mathematically that allows us to very easily calculate the components of the metric in that particular coordinate system. However, there might be a much more physically useful coordinate system, and our equation for how to transform the components of the metric allows us to calculate the components of the metric in a much more complicated coordinate system, which might be much more physically useful, providing we know the metric in the simpler coordinate system, and we have some transformation rules between the coordinates of our different coordinate systems, which will all be encoded within our Jacobian matrix. And to give a kind of concrete example of this, a very simple coordinate system to use is the Cartesian coordinate system. The thing that really makes it simple is in the Cartesian coordinate systems, the basis vectors don't change from one point to another, so their derivatives are 0, and also because they don't change, we can just decide that the vectors are always unit vectors, which means that, in a Cartesian coordinate system, at least for flat space, our metric is just written or expressed as the identity matrix, a very, very simple representation of the metric. And that might be useful if we were describing, for example, the passage of matter through a gamma ray burst, like you can see on the left-hand image, where the gamma ray burst is principally along one spatial axis. However, when we're doing general relativity, we tend to be interested in very strong gravity, so we're interested in the space-time around spherical objects, because due to the gravity they've contracted into a sphere, and therefore we would expect the space-time around these objects to have some kind of spherical symmetry, because the object itself has a mass distributed with some spherical symmetry. And so a much more useful coordinate system than a Cartesian coordinate system is some kind of curvy linear coordinate system like spherical polar coordinates. And the thing with our equation for converting the components of the metric is now we have a recipe where if we know the components of the metric in the Cartesian coordinate system, we can find it in the spherical polar coordinate system, even though how the basis vectors change in a spherical polar coordinate system is a lot more complicated, and therefore it's a lot harder to directly get the components of a metric within a spherical polar coordinate system than it would be in a Cartesian one. So, that's why we would want to transform the components of a metric to calculate it firstly in a mathematically simple coordinate system, and then get the components in a much more physically useful coordinate system. So we talked now about vectors and metrics, and I've mentioned briefly, both at the start of this video, that there are vectorial objects called one-forms. I also mentioned a little bit ago that an inverse metric could take the components of a vector and turn it into the components of a vectorial-like object, but where the components have the indices on the downstairs. And these are components of one form, so it's about high time I talk a little bit about what one forms are and how they are different from vectors. So we've talked a little bit about tensors, and we've talked, when we've done that, about vectors, which have a contravariant relationship between their basis vectors and their components. We've talked about the metric tensor, and we talked about how these things transform. But there's one more type of tensor that is worth talking about that I haven't yet. And this kind of tensor is a generalization of the idea of a gradient. It measures how quickly something is changing. And this is very important in the context of things like, general relativity, because we want to consider how, for example, vectors might change as we move them across a manifold. We might want to consider how matter moves across space, and therefore how density and things fluctuate. So understanding how we talk about gradients, in other words, some measure of rate of change, is very important. And we do it through something called the covariant derivative, and I'll talk about the covariant derivative either in the next video or the one after. But the covariant derivative is like a generalization of the idea of a gradient, but just to a curved manifold. But the gradient, whether the manifold is or is it curved, is an example of a one form. But what is, more generally speaking, a one form? If I give a most general overview of it, in case we encounter other kinds of one forms during this playlist. So a one form is a function that takes in a vector and gives you out a scalar quantity. Now, if we're thinking of operations we've looked at in this video where we have a vector and we get a scalar quantity, we can see that a one form will have something to do with the metric and finding the distances between points. And kind of building on that, if we remind ourselves about the definition of the square of the distance between 2 points, so between points at the tips of our vectors A and B, we defined it according to this relationship, where we can see our components of our metric tensor and the components of our two vectors. And, we can pull a one form from this, because if we define a one form to be vector A dot, we can see that if we act vector A dot, this function, on another vector, like vector B, we do get a scalar by definition. So A dot is an example of a one form. But if we're going to find the components of this one form, well, the components, if we just look at our definition for the scalar product, our components are just going to be G mu nu, A nu. And using the idea that indices, well, upstairs and downstairs indices that are the same kind of cancel out, we can write it in index notation. We can write the components of a one form as A mu. So notice, if the index is on the top, and we just got one index, that's the component of a vector. If the index is on the bottom, and there's only one index, that's a component of a one form. And a one form and a vector are two different things. Because we get, for example, a vector by operating a component of a metric tensor on a component of a vector. So clearly, the component of a one form is different to the component of a vector, because because the component of a one form is this interplay between vectors and our metric tensors. So this is a very abstract definition, but how do we visualize this? And this is going to go back now to the idea of thinking of the gradient as a concrete example of a one form. So let's consider phi to be some scalar function, and let's say it's parameterized by a parameter t. We can ask, well, how does phi change as we change t? And phi is some scalar field. Well, it changes according to this law by the chain rule. Now, if phi, is a field with components along multiple axes, the partial derivatives are different from the ordinary derivatives. And this is very important if we're distinguishing between components of a one form and components of a vector. So because phi and t are scalars, d phi by dt is going to be a scalar quantity. Now, dx mu by dt are going to be components of a vector, because we're seeing how quickly a vector changes with respect to a scalar, and that's just going to give me another vector. I mean, for example, if we've got a log line, which is like the trajectory of for position spacetime parameterized by proper time t, or tau, then the rate at which that log line changes with respect to tau, so for velocity, is like the gradient of that curve, and for velocity is a full vector. It's not a full one form, it's a full vector. So dx mu by dt is, it's how quickly a vector changes, so it's going to be a vector itself. But we said when we act a one form on a vector, we get a scalar. So since dx mu by dt are components of a vector, and d phi by dt are components of a scalar, that must mean the partial derivative of our scalar field with respect to x mu, that partial derivative is a component of a one form. And if we put all our components of our one forms together, we end up with our overall one form, and that overall one form would be the gradient of our scalar field. So the gradient of a scalar field is an example of a one form. And this is one of the places where it's very important to differentiate between partial derivatives and ordinary derivatives. But it turns out when we're dealing with curved space-time, due to the fact that there isn't really any good single coordinate system because our manifold is curved, defining partial derivatives, the partial derivative would no longer act like a tensor. So if we wanted a one form on a curved manifold, we would need some version of the gradient that would take account of the curvature of the manifold. And, an example of a gradient-like thing that does that is the covariant derivative. And so the covariant derivative is the type of one form we'll be using properly when we get on to, applying all of this to, curved manifolds and curved space-time. But anyway, that's everything for this video. I know this video has been a fair bit of maths. I will do some, extra mini videos to show you how you can calculate with this maths, because I'm aware there's a lot of symbols in algebra here. But the focus has been to give you a geometrical understanding of the metric vectors and also one forms, and hopefully it's accomplished something like that. It's worth saying all of this stuff is pretty advanced, so if you have to look back over this video again, don't be disheartened. General relativity is a very advanced topic and very abstract. But we'll be using this maths later on, which will hopefully make it less abstract and more concrete. But we have to firstly encounter the maths before we can apply it. But yeah. But I hope this video has been helpful. I'm wishing you a really good week ahead, and I hope to see you for some more wonderful physics hopefully soon.